Welcome back to the course of chemical crystallography. In the previous lecture, we learned about the linear density, repeat distance, and then we tried to calculate the planar density of various crystallographic planes in case of simple cubic, body-centered cubic lattices, and I left it for you to work out for the face-centered cubic lattices. So today we will try to understand these three basic systems: simple cubic structure, body-centered cubic and face-centered cubic structures, and we will try to calculate their packing fractions and things like that. So in case of simple cubic lattice, as we have already indicated, there are 8 atoms located at 8 corners of a cube, and this is shown here in this particular slide. So if you look at any atom that is marked here as red, that particular atom has 6 nearest neighbors from 6 different unit cells. So the left, right, back, front, top and bottom corresponds to a coordination number of 6 for every corner atom of this simple cubic structure. Remember, you have only corner atoms in case of simple cubic structures. So when we try to calculate the atomic packing fraction or atomic packing factor, we write APF equal to volume of the unit cell divided volume of the atoms in the unit cell divided by volume of the unit cell. So now in case of simple cubic structure, this is calculated to be 0.25. How? In case of simple cubic, if you note that the corner atoms touch each other along the face edge, along the edge direction, which is A. So we can write A equal to twice R, and from that you can calculate the volume of one such atom, because every atom sitting at corner contributes 1/8. So altogether 8 corner atoms contributing 1/8 gives you 1. So number of atoms per unit cell is 1, and the volume of that atom is 4/3 pi r cube. R is half of A, so 4/3 pi r cube is the volume occupied by those atoms, and the volume occupied by the unit cell is A cube. So the result turns out to be just 0.52, which means in case of simple cubic there are lots of void space in the lattice. So when we go to the body-centered cubic lattice or body-centered cubic structure, as we write it as BCC, in this case the close packed direction is the body diagonal. So from one corner through the center atom to the other corner, the atoms are touching one another, considering them as hard spheres. So in that case, if you consider the atoms located at the center of the body, center of the unit cell, then you have 8 such atoms which are touching to this particular central atom. So that is why we write that the coordination number of a body center lattice is 8, and the body center atom has coordination number 8. So in case of body centered lattice, the atomic packing fraction turns out to be 0.68. How? Because the body diagonal is capital R, which is, body diagonal is √3a, which is equivalent to 4r. R is the radius of each atom. And then every unit cell contains 1/8 contribution from the corner atoms. So there are 8 such atoms at corner, so contributing to 1, and then the body center atom, which is totally inside the unit cell, so it contributes to 1, so you have total 2 atoms per unit cell. So now we try to calculate the atomic packing factor here. So this is equal to 2 times, that is 2 atoms per unit cell, the volume of the atom. So now this R, capital R, is √3 by 4a. So the volume of one atom is 4/3 pi root 3 by 4 whole cube, and the volume of the unit cell is a cube once again. So if you do this calculation, you will find that the result comes out to be 0.68. It means this is slightly more compact packing compared to the simple cubic lattice. So now if we try to see what happens when it is face-centered cubic lattice. In case of face-centered cubic lattice, the close pack direction is your face diagonal, which means along this face the atoms are connected to each other. So in case of face-centered lattice, the coordination number is 12. That means every atom has 12 nearest neighbors associated with it. So in case of this face-centered cubic, the atomic vacuum factor for FCC turns out to be 0.74, highest among all the three. So how do you calculate that? You see again the face diagonal, which is root 2a, corresponds to R, 2R and R, which means the length of the face diagonal turns out to be 4R, which is equivalent to root 2a. And then the unit cell contains 4 atoms per unit cell. How? See, the face atoms contribute half, and there are 6 such faces. So those 6 such faces contribute to 3, and 8 corner atoms contribute 1/8 each. So 8 into 1/8 gives you 1. So 3 plus 1 equal to 4. So then we calculate atomic packing factor again in the same manner, 4 into 4/3 pi r cube, here r equal to root 2a by 4. So then if you compute, this turns out to be 0.74. So this is the maximum that one can have in case of these 3 different packings. So in case of face-centered cubic and hexagonal close pack structures, this atomic packing factor is turned out to be 0.74, and this is the highest packing fraction that one can achieve. The most efficient packing for equal sized spheres. But now we need to understand the stacking in HCP, that is hexagonal close pack, and stacking in FCC, the face-centered close pack. If we assume that the first layer is placed like this, then there are 2 ways the second layer can be placed. So when you place the second set of atoms like that in gray, it is like AB, AB, AB packing. So the third layer can be placed on exactly on the yellow, or third layer can be placed like the red. So that means there are 2 ways one can put the third layer, and that third layer decides whether it is hexagonal close pack or a face-centered close packing structure. So in case of hexagonal close packing, it is AB, AB, AB type of packing, and in case of FCC, it is ABC, ABC, ABC type of packing. So both of these structures share common features. The atoms are closely packed. Each atom has 12 nearest neighbors, so that is the coordination number 12. To see this packing, we can use a simple demonstration. This green layer indicates the lowermost level. In that, we are designating some of these points with blue dots, and we will see that they end up showing as tetrahedral interstitials. So now I am placing one layer of red dots which are alternate with respect to the blue, and it will correspond to the octahedral interstitials. So once we place the another layer of the spherical atoms, which are now represented in blue, you see that when we look at this region, here we have 3 greens, 1 blue, and then at the center we have 1 blue. So that central blue atom corresponds to the tetrahedral interstitial like this. If we concentrate at a different location where you can see this arrangement, for example, when we try to see here the arrangement at this point, you have 3 green atoms at the lower layer, 3 blue atoms at the upper layer, and in between these 6 atoms you have 1 central red atom located at the octahedral interstitial. So when you place 2 layers of atoms, you generate 2 different types of sites. One is called the tetrahedral site or tetrahedral interstitial. The other point is octahedral site or octahedral interstitial. What is the difference? The tetrahedral interstitial has coordination number equal to 4, while the octahedral interstitial has a coordination number 6. So these interstitials are also termed as holes or octahedral holes or tetrahedral holes, and we can think of generating different ceramic structures where you have a cation and anion, and in general the anions are larger in size, cations are smaller in size, and as a result the cations occupy these different interstitial sites. So when we have determined that there are different types of holes available, now we must decide which sites are occupied by a given atom and how many sites are occupied. The first point, which sites are occupied by a given atom, is decided by the radius ratio, that is the ratio of the radii of cation to anion, whereas the number of sites inside a lattice occupied by a number of atoms is decided by the stoichiometry and charges on those cations and anions. This we will see in future slides. So let us see what is the ideal radius ratio for cation and anion for octahedral site. So in case of octahedral site, the central atom, which is marked here, in red, this central atom is connected to 4 atoms on this plane. So the distance d from the center of one anion to the center of other anion through the cation, that distance d is equal to 2r of cation plus 2r of anion and 2r of cation. So once again, this distance d can be calculated as this distance is 2r as we indicated. So the value d is 2r anion square plus 2r anion square and square root of that. Therefore, we can equate these 2 equations and calculate the ideal value for cation to anion radius ratio for an octahedral site. In the same manner, it can be shown for tetrahedral site, the value is 0.225. I would like to leave it to you to determine how can you calculate this value. So now we apply this radius ratio rule. As we know, the cations are generally smaller than anions. So in general, Rc by Ra is smaller than 1. So now to have a stable ceramic structure, anion surrounding a cation must touch each other. So now there can be 4 different situations. In the situation 1, where the cation is touching all the 4 anions, but the cation is large enough to drive these anions away and generating a gap between the anions. So this is one of the stable conditions where the structure is stabilized. Here is the cation is slightly larger than ideal radius ratio value of that particular crystal packing. If the cation is perfectly fitting inside the interstitial site, that means the cation and anions are touching along the diagonal. Anions are also touching each other in all the 4 edges. So this is the ideal situation of ideal ratio of cation to anion, and this is the most stable structure. But once the cation is too small, it is not touching any of the anions, and the anions can only touch each other. In that situation, the cation can rattle. That means the cation can vibrate inside the lattice. As a result, the structure becomes unstable, and we don't have a large number of structures having this type of arrangements. So now we need to learn what is the coordination number and what is its relationship with ionic radius. So coordination number increases with Rc by Ra, that is the radius of cation by radius of anion. So here we have a small table. On the first column, we are giving the value for R cation versus R anion, the ratio, the corresponding coordination number, and a probable structure representing that. So when it is this cation to anion ratio is 0.15, that means cation is extremely small compared to the anion, then the coordination number is 2, and you see a situation like this. When this coordination number falls between 0.15 and 0.225, the coordination number is found to be 3, and the situation arises like that. The next higher ratio is between 0.25 to 0.41. This corresponds to the coordination number 4. So when you have 4 coordinated system, coordination number 4, this gives rise to a tetrahedral interstitial, and that is seen in case of zinc blende structure, ZNS structure. We will discuss this structure in detail in future slides. But what we can see here is that you have sulfide atoms occupying the face center positions, the 8 corners and face center positions, and zinc atom occupying the alternate interstitial sites. Those are tetrahedral interstitial sites. So now when the radius ratio increases to about 0.41 to 0.73, the coordination number 6 is achieved, and it represents the octahedral arrangement, and that is seen in the most common crystal structure of sodium chloride. Sodium chloride structure, as you know, is interpenetrating face-centered lattice. We will see it through an animation as well in future slides. When the radius ratio is close to 1, then the coordination number increases to 8, which means you get a structure like cesium chloride structure, where you have a simple cubic lattice of cesium simple cubic lattice of chloride and a cesium atom sitting in the middle. So this is another example of a simple cubic lattice which is actually interpenetrating simple cubic lattice. So now let us see how one can calculate the radius ratio, cation to anion ratio for a coordination number 3. So here we have three anions, the blue ones are the anions, and we have a red cation at the center. So now if we construct a triangle ABC, which is equilateral triangle, in that we have the angle PAO as alpha. What is that? We have dropped a perpendicular from O to AB and made it OP. So as a result, AP equal to PB, AP equal to PB equal to the radius of the anion, and AO is nothing but radius of the anion plus radius of the cation. So now if we do AP by AO, which is cos alpha, and alpha is 30 degree because this is an equilateral triangle and the line AO bisects this BAC angle. So an angle of 60 degree is bisected, that means it is 30 degree. So what we can do is AP by AO equal to AP is RA, AO is RA plus RC, which is again equal to cos 30 degree, which means root 3 by 2. So then if we simplify this, we can then calculate the ideal radius ratio for a coordination number 3. This concept can be utilized when you try to calculate the ideal radius ratio for the tetrahedral interstitial. When you have a tetrahedral interstitial filled with a cation and you have 4 anions forming a tetrahedra, you would need to utilize this type of simple geometrical method to find out the corresponding radius ratio for the cation and anion in case of tetrahedral structures. So now when we try to understand the tetrahedral and octahedral sites for face-centered cubic lattice, here in this figure, the figure above has a face-centered lattice where you have black dots at 8 corners and 6 faces representing the face-centered cubic lattice. So in that, in the middle, we have identified one point, which is the octahedral hole or octahedral site. That octahedral site indicates that this atom has coordination number 6, and there are 12 such octahedral sites present in these lattice, because you have 1, 2, 3, 4, all the edge centers, all the edge centers and all the edge centers. So total 12 octahedral sites along the edge centers plus the one which is at the center of the lattice. So that means you have 13 lattice sites, 13 octahedral lattice voids. Now these edge center sites are shared by 4 unit cells. As you can understand, this one is shared by this unit cell, the one which is on the next, then on the top this side, and then on the top on the right hand side. So every corner, every edge center lattice site is shared by 4 unit cells. So each of them contribute 1/4, That means you have 12 such sites, every one contributing 1/4 is equal to 3 plus 1 equal to 4 positions per unit cell. Now if we look at the lower representation of the same face-centered lattice, where you have atoms at 8 corners and atoms at 6 faces. So now the positions which are marked here in red are this one, and so on. All these points correspond to the tetrahedral sites. What are the coordinates of those sites? I have written one here. Actually, these sites are 1/4, 1/4, 1/4. Suppose this one. Then you have one more which is 1/4, 3/4, 1/4. Then 1/4, 3/4, 3/4, and 1/4, 1/4, 3/4. These are those 4 lattice points in the lower region, and the upper regions are 3/4, 1/4, 1/4, 3/4, 3/4, 1/4, 3/4, 3/4, 3/4, and 3/4, 1/4, 3/4. So inside this lattice there are 8 such locations which are tetrahedral sites, and each one of those is inside the unit cell. They are not shared by other unit cells like the face, like the edge center atoms in case of the octahedral sites. So they correspond to the 8 number of cations that can be placed inside the lattice. So in case of cubic closed packed structures, the FCC structures, anion arrangements and the summary of possible cations is listed here. So number of anions per unit cell is always 4, as you can see, and then if we start filling the octahedral sites, if we fill all the octahedral sites, that means 100% of octahedral sites are filled, you have 4 cations as well. Then the stoichiometry turns out to be Mx, and the example is a sodium chloride structure. The other extreme point is when there are no octahedral site occupied, but all the tetrahedral sites occupied, we get a formula of M2X, and we see a K2O structure which is like this: a face-centered cubic lattice with a different arrangement of cation and anions, giving rise to different molecular formula or stoichiometry, and it is one of the example is K2O. In case of third set, where there is no octahedral site occupied and only 50% of the tetrahedral sites occupied, once again we end up getting Mx type of stoichiometry, 1:1, but here the interstitials are tetrahedral interstitials which are filled, and 50% of those are filled. So the cation-anion pair is an example of that kind of structure is zinc sulfide or ZnS. When the corresponding reverse happens, that is 50% of the octahedral sites are occupied and not a single tetrahedral site is occupied, so you have 2 cations and 4 anions, That means you have MX2 type of structure. So this is an example of cadmium chloride structure. The other theoretical possibility is both tetrahedral, octahedral and tetrahedral sites are 100% occupied, so one should have this type of formula M3X, but till now there are no such known structures having this type of coordination geometry. The last type that one can think of is 50% occupied in case of octahedral site and 12.5% occupied in the tetrahedral sites. The formula turns out to be M3X4, and there is one type of example, a structural type called spinels, which we will discuss in the next class. This MgAl2O4 corresponds to a spinel structure where a part of the octahedral sites are filled and a very small portion of the tetrahedral sites are filled. So in today's lecture, we have learnt about the atomic packing factors for simple cubic, body-centered cubic, face-centered cubic. We have learnt how to calculate the radius ratios for different types of coordinations for cation and anion, and then we understood what are the different types of interstitials, tetrahedral and octahedral interstitials. So from here we will continue in the next lecture.